Hello everyone. On this video we will be looking at the definition of what is called a dot product of vectors. Alright, so to give a quick definition, the dot product excuse me, of, let's say, vector A that has the components 1 and 2, and let's say vector B, which of course has two components we'll call B1 and B number 2, is A dot, or the dot product of A and B is equal to multiplying the first components, so A number 1 and B number 1, plus then multiplying the second components, A number 2, B number 2. Of course, this is for two-dimensional dot products, but when A is equal to first component, second component, and the third component, and B vector is equal to first component, second component, and third component, then the dot product of A and B is equal to multiplication of the first components plus multiplying the second components plus multiplying the third components. Okay, which is the dot product when you have three dimensions. Okay. Now, if you notice, the dot product or in some textbooks, not many, but in some textbooks, they will call it the scalar product. Of two vectors will result in a scalar. Okay, so that means when you calculate the dot product, you will get just a scalar answer. You won't get another vector. All right. So let's look at a few properties of dot products. Okay, so the first is the commutative property. Which, just like with anything else, commutative property just means you can switch them up. So A dot B is the same as B vector dot A vector. Okay, and property number 2 is the distributive property. Okay, so if you have the dot product of A and you have the sum, or you can have the difference, B, it could be plus or minus two other vectors. And that's equal the dot product. A and B, I went a little bit ahead. And it's either plus or minus, depending on which one is in here, the dot product of A and C. Okay, so it's kind of just the distributive property. Okay, now the third property is if you multiply a dot product by a constant. So some constant times the dot product of A and B, you can actually just multiply that constant by either one of those and you'll get the same answer. So that's either equal to a constant times A times the dot product of B, or you can multiply that constant times the B. So you have A, the dot product of that constant. Okay, jumping ahead a little bit. There we go. That's better. Okay, so you can move that constant to either one. Okay, so the fourth will be the zero vector property. So the zero vector and the dot product of the B vector will just equal 0. Not zero vector, but actually 0. And the fifth property, if you have the dot product of the same vector, that will equal the magnitude of that vector squared. Okay, so we'll do a quick proof of the fifth one. So proof of number 5. Okay, so starting at this end, we already know that since the magnitude of a vector squared is equal to, you have the magnitude, which is just the square root of the first component squared plus the second component squared plus the third component squared. And that whole thing is 4 squared. Okay, now the square and the square root will cancel each other out, which just leaves the first component squared plus the second component squared plus the third component squared. Okay, so just moving that over a little bit. This, you can actually rewrite it as the first component times the first component plus the second component times the second component plus the third component times the third component. Since they're each just squared, we're just multiplying to each other. Okay, so when you have these being multiplied to each other, you can just rewrite that as the dot product of a vector and a vector. So we see that the magnitude of the vector squared is just equal to the dot product of that vector to itself. All right. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and start on a few examples. All right, so let's say, for example, running out of pencil lead here. There we go. Let's say for the a vector that's equal to 2, -2. B vector that's equal to 5, 8. And the C vector that's equal to -4, 3. Find, okay, let's say for problem A, we want to find the dot product of A and B. Say for problem B, we have the dot product of A and B times the vector C. Say for problem C, we have the dot product of A and 2 times vector B. And let's say for problem D, we want to find the magnitude of the C vector squared. All right, so let's go ahead and get started on this. Okay, so for problem A, we have the dot product of A and B, okay, which is really just the dot product of 2, -2, and 5, 8. Okay, now remember with the dot product, you just multiply the first component, so that's 2 times 5, plus, and you multiply the second component, so that's -2 times 8. Oh, put that there. Okay, so we have 10 plus -16, which is -6. Okay, so the dot product of A and B is -6. All right, so for problem B, we have the dot product of A and B times the C vector. Okay, well, this one should be pretty easy because we already figured out the dot product of A and B is -6. So this is just -6 times the C vector, which is -4, 3. Okay, so we have -6 times -4, that's +24, and -6 times +3 is -18. All right, so for problem C, we have the dot product of A and 2 times the B vector. Okay, now remember from the property where we can move the constant around, so if you remember, constant times the dot product of A and B can actually equal the dot product of A and that constant times the B vector. So that means we can just pull that constant right on out. So that's just 2 times the dot product of A and B. And we know the dot product of A and B is -6, so that's 2 times -6, which is -12. Now, if you wanted to, you could have multiplied 2 times B, so that could have given you the vector 10, 16, and then you just find the dot product between A and 10, 16. Sorry about that. So between A and 10, 16, and that would have given you the same answer. This is just kind of a shortcut using the properties. And problem D, move that up. The magnitude of the C vector squared. Okay, so we know that the magnitude of the C vector is just the square root of each of the, move that down a little bit, each of the components squared, so that's -4 squared plus 3 squared. We have -4 squared plus 3 squared. And that whole thing is squared. Okay, so since the exponent and square root cancel each other out, we have -4 squared, which is 16, plus 3 squared, which is 9. So we end up with 25. All right. Okay, so this video kind of introduced the properties. Okay, so hopefully it made sense, and I will see you on the next video.